Hello, good morning, everyone. I'm really very happy to be with you today. This lecture is very important. I had to record it from home since we have some problems due to the short time and the huge amount of information that I wanted to give it to you in this video, and I needed to do this as fast as possible. Hopefully, it will be clear. And as you know, all our course records and recorded lectures, you will find them on my YouTube channel, as you know. And all the resources, you will find them on Moodle, either the main slides, PDFs, or even a recorded version of the main lectures. You will find them over there with no problem whatsoever. Okay, let's follow up. I want to summarize the major problem that faces us when we come to the point of the second derivative and it is equal to zero. This point is really very critical and it's really very important. So we are in the part that we are seeking to have an optimal value for a function, and we already differentiated the function for the first order derivative. Putting it equal to zero, we have the critical points, and we are investigating the nature of these points. And for the second derivative, once it is equal to zero, we will be in the middle of roads. So let's see how to deal with it in specific and how to go to further investigation if needed. So the first thing to remember is how to classify the critical point when f double dash of x equal to zero, or the Hessian matrix in multivariable functions, it's equal to zero. So this is mainly the two main points that I want to speak with you about. Remember, first of all, we will have to get our critical points, and this will happen when we get f dash x equal to zero. And this is simply can be done by equating the first derivative equal to zero, solving this equation or this system of equations in order to get the critical points, which are candidates for either extremum point, minimum point, maximum point, or a saddle point. Step number two, let's check the second derivative. If double dash x doesn't equal to zero, which is very, very good, so our life problems will be solved. As at this point, we will substitute by the critical points at f double dash x, as you can see. And if the result of this function is greater than zero, then you will have a minimizer. If the value is less than zero, then you will have, less than zero, you will have a minimizer. Greater than zero, you will have, uh, I'm sorry, if you have f double dash x and it is negative, which is less than zero, you will have a maximizer. If it's greater than zero, you will have a minimizer. Okay, what's gonna happen if f double dash equal to zero? In this point, we will have an inclusive result, and we will need to proceed to higher order derivatives in order to check the nature. So let's compute higher order derivatives of x naught. And all of this was covered previously in the previous lecture, but I wanted to go through it with you as we are going to multivariable functions and what's going to be the case over there. First of all, I will find the lowest order derivative fn of x such that this first non-null derivative doesn't equal to zero, which means, of course, we will differentiate more than n equal to 2. تاني يا شباب، انا بجيب الفيرست اوردر ديريفاتيف بساويه بزيرو، بجيب كريتيكال بوينتس، بجيب اف دبل داش، بعدين بعمل سبستيتيوشن. لو طلعت فاليوز خلاص، لو اقل من صفر يبقى اذا انا عندي ماكسمايزر، اكبر من صفر يبقى عندي انا اسف، اقل من صفر يبقى اذا عندي ماكسمايزر، جريتر ذان زيرو يبقى عندي مينيمايزر. خلاص اتس دان. المشكله بتحصل لما اف دبل داش بيساوي زيرو. في الحاله دي انا هبدا اعمل ديريفاتيفز بالتاكيد هتبقى اكبر من 2، فهروح للثيرد اوردر فورث اوردر ديريفاتيفز وهبدا امشي في الاتجاه ده. So find the lowest order derivative. هحاول اوجد اقل order derivative which is not equal to zero. اول تفاضل مش هيساوي الصفر، طبعا اكبر من 2. Okay, use the following rule. If n is odd, x node is gonna be inflection point, not an extremum. يعني لو اول تفاضل مش بيساوي الصفر كان على رقم فردي، يعني التفاضل الثالث كان مش بيساوي صفر، التفاضل الخامس كان هو اللي مش بيساوي صفر، ده اول تفاضل doesn't equal to zero. If this happens على طول you are done. It's a point of inflection. You don't have to do anything else. Okay, but if it is even and the value of the critical point of this is greater than zero, then you will have local minimizer. Less than zero, you will have a local maximizer. And this is really very important. In summarization of these steps, let's see an example about what we are talking about. The example that I will go through it with you is f of x equal x to the power of 4. So getting the critical points, it will be really very easy. All you have to do is to get the first derivative of this function. I have x to the power of 4. So once you differentiate it once, you will have 4x cubed. Once you put 4x cubed equal to 0, you will have your critical point at x equal to 0. It's very, very simple and very clear. يبقى عندي x أس 4 x to the power of 4 differentiate once هيبقى 4x cubed. ال 4x كيوب هيساوي 0 امتى؟ لما الاكس بتساوي 0. فيري جود ولا اروع. الستيب اللي بعديها روح هات لي اف دبل داش. هجيب اف دبل داش ازاي؟ 4x كيوب اعمل لها ديريفاتيف اتس جونا بي 12x سكوير. طيب لما اجي اعمل سبستيتيوشن بالكريتيكال بوينت، يعني هبدا اشيل الاكس واحط 0، يديني ان الاف دبل داش ايكوال تو 0. يبقى اذا اصبح دلوقتي التفاضل رقم 2 او السكند ديريفاتيف بيساوي 0 عند الكريتيكال بوينت. I will need further investigation. How to go through the further investigation? It's very, very simple. I will start getting the third derivative. So let's differentiate 12x squared for an extra time, which is going to be 24 of x. يبقى 24x. لو انا replaced الاكس بزيرو هيبقى third derivative هو كمان بيساوي 0 which is not ده معناه ان انا I will have to do further investigation or further derivative. So I will go for the fourth derivative. لما ده كان 24x ده third، لما اعمل له differentiation more for another time of derivative I will have 24. 24 is a positive value which is greater than 0. يبقى إذا from this point or at this point I have two main things I've succeeded in getting them. Number one, I have the first non-null derivative which happens at 4, and the value of this partial derivative is positive, so we will have a local minimum at 0. This example will help you to understand and to summarize the ideas that we did go through in the previous lecture, which is dealing with just only a function in one variable, trying to explore the critical points. When the process failed at the second derivative, I will have to search for third derivatives. Once more, this is really the key for the next investigation in multivariable functions. To need a lot of efforts from us to understand it and to digest it very well. So now it is the time to understand this main point. Once more, I want you to know that once f double dash x equal to 0, I will have to get more derivatives. I'm searching for the first, once more, for the first null derivative that will exceed the second because the second is failed. So if it was odd derivative, the test will be inclusive. The test will mean that we have a saddle point and that's it. If the first derivative was an even number, I will substitute by the critical point in this in this even derivative, whatever the order. If it was greater than zero, I will have a minimizer. Less than zero, I will have a maximizer of at this minimum or at this critical or stationary point. Doing exactly the same thing, but on the other hand, for the multi-variable functions. Let's go through it. Extremum points and the non-null Hessian matrix classification. I want you to remember, based on the Hessian matrix, اعتمادا على الهيزيان matrix اللي هي بتريبريزنت السكند اوردر derivative for us، انت قدامك اكتر من حل. Either to use the determinant of the Hessian matrix to classify, or to use the definiteness or to classify the Hessian matrix from the point of view, is it a positive definite, negative definite, indefinite, positive semi-definite, or negative semi-definite. طيب لو انا عندي الهيزيان matrix was positive definite, I will have a strict local minimizer at f, and that's the shape of a local minimizer. If I have a negative definite, then I will have strict local maximizer at this critical point, as we will see. If I have a saddle point of f, a not an extremum, but the problem will arise once you have a positive semi-definite or the negative semi-definite. Positive semi-definite, it means you will be in between two cases, a local minimizer or a not extremum at all, and the contrary will happen when you have negative semi-definite classification, which means you may have local maximum or extremum point of f. Of course, that's the Hessian matrix. In this part, and also where we, in the previous lecture, I tried to put the light and to tell you that you need to understand very well the link between the quadratic classification of the Hessian matrix and also the classification of the Hessian matrix regarding the positive definite, negative definite, and so on. This is why I want you to remember the following couple of slides. We already did go through them. You can have more problems on this part and with a lot of explanation in the previous lectures. So now for the principal minors. Okay, I want you to remember that if I want to know the nature of the Hessian matrix, if it is positive definite, negative definite, positive semi-definite, negative semi-definite, I can do this either by getting its eigenvalues and looking to the nature of these eigenvalues, or to use the principal minors, of course, the eigenvalues of the Hessian matrix, or to use the principal minors as a leading or a way in classification of the nature of your Hessian matrix. So a principal minor of a matrix is the determinant of a matrix which results from deleting one row and the column with the same indices. And that's to identify the principal minors. So let's assume that we have this symmetric 3 by 3 matrix. Remember, if I want to have the first order, then I will get the determinant and I will start eliminating two rows. Here we go, two rows and two columns from the bottom of this determinant. And this will give me the first order or the first value of the principal minors of order 1, which is negative. And for M2, I will do the same, eliminating the first and the last row and the first and the last column, and this will leave me with -3. Exactly the same, I will eliminate the first two rows, first two columns, and I will have -1. This is of order 1. Order 2, it means you will eliminate just only one row, one column, and you will have two rows, two columns. So if I start this elimination process, eliminating the last row and the last column, this is gonna be the determinant that I will have, which is -1 times -3 +3 -1 is gonna be 2, which is a positive for the minors of second order, but eliminating the two middle row and column, I will have -1, -1, 1, and 1, and the result will be 0. I will have, for the third one, I will eliminate the first row and first column, and this is the determinant that I will have as it appears in front of you. Now to the third order, which means I will try for a 3 by 3, I will try to evaluate the value of the determinant overall, which is really very simple. All I have to do is to either by Sarah's rule or by the Gauss method, just considering any row or any column, just eliminating, as you know, in linear algebra, and you are very good in this. We studied linear algebra before, and you know how to deal with it. So it's a -1, eliminate the first row, first column. You will have this 2 by 2, then minus, which is related to the sign of the determinant, eliminate the first row, second column, and you will have the second determinant, and so on. So now I have the sign of or the values of the various principal minors. According to this, I can do this classification. So now, based on the sign of the principal minors, we can determine the type of the quadratic form. In order to do the type of the quadratic form, I will do the positive definite if I have all the principal minors are greater than 0. So it's going to be a positive definite quadratic form. Positive semi-definite will happen if some of them equal to 0. يبقى لو انا عندي كل الارقام موجبه على طول هيبقى عندي positive definite. Some of them is equal to 0 يبقى اذا directly you will have positive definite, positive semi-definite. I'm sorry. طيب خلي بالك بقى لو الاود اوردر، لو الاود اوردر بتاع البرنسبل ماينورز كان less than 0 لكن الايفن اوردر is greater than 0 I will have a negative definite. طيب لو كان في بعضهم بيساوي zeros on the same rule I will have negative semi definite. طيب لو كانت الساينز بتاعت البرنسبل ماينورز فيها بوزيتيف وفيها نيجاتيف يبقى اوتوماتيك على طول في الحاله دي انا عندي indefinite type. اسهل من البرنسبل ماينورز اني اعتمد على الليدنج برنسبل ماينور، والليدنج برنسبل ماينور بيتعمل عن طريق انك بتإليمينيت الروز والcolumns from the bottom of your matrix or your Hessian matrix. بس خلي بالك ان انا دايما في الليدنج برنسبل ماينورز I may need to check all the principal minors. يبقى تاني once more in the leading principal minors it is clear, it's going to be simple, it will appear directly. I need this information desperately in the coming slides. If failed, I will back to the principal minors in order to identify the type of the definiteness of the Hessian matrix. So now once more, if all the leading values is positive, is greater than 0, then you will have a positive definite. Okay, but if I have the odd order of the leading principal minors are negative and the even ones, the even order is positive, that's a negative definite, and that's a huge difference. Remark that, or be careful from that. If any of them equal to 0, then we will need the sign of the principal minors to charge or to judge what's going to be the situation. And this is written here and explained explicitly in the previous lectures. Okay, once more, if the signs of the leading prevent Q, the quadratic form, from being positive definite, positive semi-definite, negative semi-definite, it means we have indefinite situation. And if we have leading principal minor, let's say of order to with a negative value, none of the classification lead to an even leading principal minor being negative. So it is indefinite directly. All of this information with the rest of our work will work together in order to identify the classification of the extremum points that we will need. Okay, candidates to extremum points. This is really, or this paragraph is important. You will have to read it very good and to digest it. If A is an extremum point, يعني لو ال A دي نقطة حرجة, which means f dash equal to 0 of a differentiable real function with an open domain, so it's not restricted domain, it's an open domain, then A is a stationary point of f. يبقى ال A دي من البوينتس الستيشنري بتاعت ال F. That's the gradient vector of f at A is null, وده الفيرست ديريفاتيف. ده اللي انا واخده قبل كده، ان انا بمسك اي فانكشن بجيب الفيرست ديريفاتيف، بحط الفيرست ديريفاتيف بيساوي زيرو، بجيب الكريتيكال بوينت either from one equation or from a system of equations, as we will see. If A is a stationary point of f, then A may be or may not be an extremum point. Okay, let's do the check. هنا طبعا بيديك الديسكريبشن. This is the description of the general situation. F maps elements from the domain of Rn into R. F is differentiable function. A extremum point. We can get the gradient vector, and at A at the critical points it's equal to 0. Everything makes sense at the time being. And the gradient vector is equal to 0, which will lead to an extremum point or may not to. Let's discuss the shape and the case of this function, which of course a function from R2 mapping elements into R. And as you can see, we have x cubed minus y cubed minus 3x squared plus 3y squared. Okay, now we are moving from R2 into the one dimension. F is a polynomial, so it's a C infinity. You can differentiate it as much as you want till it disappears. That's a look or a specific look in the critical spot in our graph. And that's, let's say, a look to our graph in 3D, but from away view. This point, you will find it at the middle of the shape. As we look to this shape, we may have maximizer, minimizer, and we may have also other critical points. We will check and see. Okay, now we will have to go through my analysis. My analysis will start once we get the gradient vector as we know, and plotting this gradient vector equal to 0. Let's do so. So the first thing now is to get the gradient vector, plot it equal to 0. Of course, this is f dash, the gradient vector times uv equal to 0. The gradient vector is perpendicular on the field vectors at this point. Okay, let's back to our problem once more. Here's our problem, and it is a polynomial of C infinity and the differentiable. I will get the gradient vector of f, and putting this first derivative equal to 0, and try to get the stationary points that we are seeking. So now once more, try to get the first derivatives, the first partial derivatives for this function. Differentiating with respect to x, it will give 3x squared minus 3y squared minus 6x plus a 6 over y. And all of these values will be, this is gonna be the first partial derivative with respect to x. Do it once more with respect to y, which is gonna lead to negative 3 over y squared plus a 6 over y. Here we go. Now I will try to solve this system of non-linear equations. It needs good judgment. I will need you to focus very well to understand and to see, because each problem by itself is a special case. Okay, good. I will try to catch 3x as a common from the first equation. So I will have 3 of x times x minus 2 equal to 0, which means either x equal to 0 or x equal to 2. I believe there is a typo here. There is a minor error in the sign. As you take negative 3y as a common, you will have this guy with a negative value. So actually, it's a negative 3 over y times y minus 2 equal to 0. So once you equate this, you will get x equal to 0 and x is equal to 2. And same way, same, y is going to equal to 0 or y minus 2 equal to 0, which leads to y equal to 2. Now I have probable for stationary point x equal to 0 with y equal to 0, or x equal to 0 with y equal to 2, and same way like for the other case, 2 and 0 and 2 and 2. So I have 4 stationary points, as you can see. So the first order derivative for this function developed 4 points, which probably maybe will be stationary points. I will go to the next point of our analysis. I will have to get the extremum points, the fitness, and the fitness examples, analysis for this problem. Is explaining what's going to happen. I will need to get the Hessian matrix. I will try to substitute by the critical points. I will try to see if it was positive definite, negative definite, indefinite, and what's the cases is going to happen, because we had a classification related to these cases. We already explained it previously. So once more, that's our function. And the gradient vector is already known at the time being. So it's an easy way to find its second derivative, which is the Hessian matrix. So simply, all I have to do is to differentiate 3x squared minus 6x with respect to x and with respect to y. Same way like with this guy, with respect to x and then with respect to y. So that's the Hessian matrix. Differentiating with respect to x, it will develop 6x minus 6. And differentiating the first line with respect to y, we don't have y, so it's going to be equal to 0. For the second function, differentiating with respect to x, it contains no x, so it's 0. Double derivative, or the second partial derivative with respect to x, will develop minus 6y plus 6, as you can see. Now I will use the stationary point 0, 0, 0, 2, 2 and 0 and 2, 2. Let's pick first 0, 2 and 2 and 0 and start substituting. لو انا بجيب الهيزيان matrix, if we want to get the Hessian matrix 2 and 0, I have to do is to substitute in this guy, in the Hessian matrix. So 6 times 2 is going to be 12. 12 minus 6, it will develop 6. Same way like for the second row. Negative 6 times 2 plus a 6. Negative 6 times 2, which is negative 12, plus a 6 is going to be positive 6. So once more, trying to substitute by the point of 0 and y, of 2 and 0, you will have huge matrix over here, or this is the Hessian matrix at this critical point. Let's see the principal minors, the leading principal minor. The leading principal minor of order 1 is 6, and of order 2 is gonna be 36. Both of them are positive. So it's a positive definite situation, which leads to you will have at 2 and 0, the quadratic form is greater than 0, and then you will have local minimizer. يبقى أول ما بعوض الاثنين وصفر، بلاقي على طول إن الفاليو بتاعت الليدنج برنسبل ماينرز كلهم أكبر من الزيرو، وبالتالي على طول ده معناه إن الأوردر 2 of derivative doesn't equal to 0, null, and it's an even order, والvalue بتاعته greater than 0 at this point، يبقى على طول f is a local minimizer. اوكي for 0 and 2 برضه نفس الكلام. لو انا حطيت x بتساوي 0 هيدي لك نيجاتيف 6، وحطيت y ب 2 هيدي لك نيجاتيف 6. طيب الفيرست اوردر، خلي بالك الفيرست اوردر leading principal minor it's gonna be a negative of 6. بعدين لما اجي اخد السكند اوردر يبقى نيجاتيف 6 تايمز نيجاتيف 6 which is gonna come up to 36. وده معناه ان الفيرست leading principal minor negative لكن السكند principal minor is positive. وده معناه على طول ان انا عندي نيجاتيف definite situation، والنيجاتيف definite situation ده معناه على طول ان انا عندي maximizer. يبقى انا from the 4 points that we are talking about at 0 and 2 and 2 and 0 2 at 0 عايز عندها minimizer، 0 and 2 عندها maximizer. We are done. But we still have another two stationary points that we didn't do the analysis around them, which is 0 and 0 and 2 and 2. نروح بقى عند 0 0 وعندي مين؟ وعندي 2 2. طبعا نروح عند 0 0. ده الهيزيان ماتريكس، دي الهيزيان ماتريكس. لما تنسرت اكس بزيرو وواي بيساوي 0 هيبقى الشكل بتاعك نيجاتيف 6 و6. تيجي تجيب الفيرست ليدنج برنسبال ماينر هيدي لك نيجاتيف. تيجي تجيب السكند ليدنج برنسبال ماينر برضه هيدي لك نيجاتيف. وده معناه على طول ان في in this case انا مش عارف I will need further investigation. اوكي، عشان اقدر اعمل ده لسبب، لان دلوقتي في الوضع اللي انا موجود فيه انا مش عارف هل دي ممكن تبقى strict local maximizer، يعني ممكن تبقى a candidate for extremum or it's a saddle point. So I will need deeper analysis when the Hessian matrix fails, as you can see. Okay, let's do this once more. At 0 0 for some عشان اقدر اعمل ده هحتاج ان انا ارجع للكوادراتيك فورم بتاعت النيجاتيف 6 و6 which have different signs، وهيبقى نيجاتيف 6 يو سكوير و6 في سكوير. بعدين هبدا احط الكوادراتيك فورمز بتاعتي واختار two directions. لو two directions of these two functions they have different analysis, so one of them is a strict maximizer, strict minimizer, and the other is strict minimizer, like the case here and it's explained briefly in the PDF, then we will have a saddle point. Okay, once more, if I want to do this, but at the point 2 and 2, same way like here at the case of 2 and 2, the first, once you substitute by 2 and 2 in the Hessian matrix, you will have 12 minus 6, which is positive. Then you will have negative 12 plus 6, which is negative 6. As you can see, the leading principal minor is positive, while the second order is negative. And if you want to get back to the quadratic form, you will have your quadratic form with different signs in the Q and the R. At Q, you will have a strict local maximizer, and at 2, you will have strict local minimizer, because 6x squared plus negative 6r squared for some directions will be less than 0, and for others will be greater than 0. Then I will have a saddle point at this point. Okay, I want to summarize these steps because it's because of it has a lot uh, 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 a lot of special cases, and it will need you to be focused directly with every step. I will need to summarize these steps. Let's do that. So, summary of the classification when you have a failure. First of all, you will get the critical point. Let's repeat the story from the beginning. I will get the gradient vector, putting it equal to 0. These points where the gradient 0 is the stationary point. We'll try to get my Hessian matrix, which is the second, represent the second order derivative for me. And I will start analyzing using the Hessian matrix. Check the determinant of the Hessian. I will have to get the determinant of the Hessian matrix. Okay, perfect. If the determinant of Hessian matrix, which is f of f double x, f double y, multiplying them together, minus f of xy to the power of 2, and this value already exists, and you have f double x. Based on this, the determinant or the sign of the determinant, and for the f of double x, I can do, as we spoke previously, an analysis about the nature of this critical point. I want to link how to deal with the determinant or the value of the test at the Hessian matrix, and also to connect this with the fitness of the Hessian matrix. This table is very, very good. So if you have the value of the determinant greater than 0 and the fxx is greater than 0, you will have a local minimizer, which stand for, from the point of view of positive definite or negative definite, all the elements of the Hessian matrix are positive definite, I will have local minimum. So that's the link between the principal minors and the sign of the value of the determinant of the Hessian matrix and f double x. If I have the value of the determinant of the Hessian matrix greater than 0, but the value at the critical point f double x is less than 0, this is going to be exactly the same when you have negative definite case, and you will have a local maximum point. When d is less than 0, you will have indefinite case, which is saddle point. When d is equal to 0, the system will be inclusive, and we will need to go through further investigation. And it is the case of inclusive in case of semi-definite cases, both of negative semi-definite or negative or or positive semi-definite. اوكي alternative use of eigenvalues عشان برضو تبقى completed all the vectors. This is how to do the analysis with the determinant. This is how to go through positive and the negative. The determinant, once it hits 0, it will stop, and I will need to use those guys, the fitness of the principal minors, of the leading principal minors, or to analyze using the eigenvalues if it is really available with you. If I have all the eigenvalues and they are positive, I will have a minimum. I'm talking about the eigenvalues of the Hessian matrix. If they are all negative, I will have a maximum. If mixed sign, it will be indefinite, so it will be a positive saddle point. Sum 0 يبقى ده معناه rest non-negative، يعني ده inclusive. وبرده في حالة انهم mixed هيبقى السيستم بتاعك inclusive and you will need further investigation. Based on the Hessian, here we go. That's the positive definite. All eigenvalues is greater than 0, local minimum. Less than 0, local maximum. Mixed sign, saddle point. F semi-definite, either positive semi-definite or negative semi-definite. ده معناه ان في بعض الايجنفاليوز بتساوي 0، يبقى تشيك higher order. 0 determinant any case، يعني معناها انه inclusive. برضو انا حبيت احط التشارت ده. This chart will summarize everything. It's a classification of the critical points using the Hessian matrix. Evaluate the Hessian matrix. لو هي positive definite I have local. لو هي indefinite يبقى عندي saddle point. لو هي negative definite يبقى local maximum. طب لو انا عندي semi definite or الديترميننت بتاع الهيسيان ماتريكس بيساوي 0، يبقى في الحاله دي السيستم is inclusive and I will need to do further investigation by getting higher orders. طيب السمري اوف ستابس لو انت حصل ان السيستم inclusive، على طول في الوضع ده اني once more بجيب دلتا بتساوي 0، ده الهيسيان ماتريكس، بجيب critical points، check the determinant of the Hessian. الهيسيان ماتريكس بيساوي 0، يعني ده معناه ان السكند ديريفاتيف تيست is inclusive failed. يبقى الهيسيان ماتريكس طلعت الديترمينانت بتاعها بيساوي 0، وفي الحاله دي انا عندي failure والسيستم بتاعي inclusive و I will have to get the higher order derivatives. The higher order derivatives it's a part of Taylor series around the critical point. So we will have a quadratic part and the R, which is the higher term, third, fourth, and so on. And this is one of the reasons that we already dealt with Taylor and Maclaurin expansions in multi-variable functions at the beginning before the part of the optimization that we may need them. Based on identifying the lowest degree of non-zero homogeneous polynomial of total k, which must be greater than or equal to 2, because k already the second order derivative failed, so I need to go through the third and fourth. If at the critical point using the sign of bk اول بولينوميال او اول derivative مش بيساوي زيرو، لو اكبر من زيرو يبقى عندي local minimum، less than zero local maximum. لو خد both sides يبقى both signs يبقى انا عندي saddle point direct. قبل ما ابدا في problem من البروبلمز very important example ومساله حلوه قوي، عايزك تخلي بالك من الايه، ان انا لما كنت بستخدم x minus x نود y minus y نود في تايلور كنت دايما بحطهم u و v عشان يخلوا الايكويشنز او الهاير اوردر derivatives في المالتي فاريبل فانكشنز يبقى easier on us. يبقى انا دايما بستخدم ده. خلي بالك ان السكند اوردر derivative دايما بيبقى double x in u square x minus x node which is x node critical point 2 of the mixed derivative partial derivative times u and v, and then once more f double y the second order or the second partial derivative of f with respect to y at v square. طيب لو ده حصل له failure I need ان انا اجيب الثird. This is the formula for the third derivative او 3 order derivative of a function زي ما حضراتكم شايفين. بجيب f treble at u cube 3f double xy u square و v، بجيب 3f of x double y at u v square، بعدين بجيب ال f differentiated 3 times at u cube. بعدين لو انا احتجت الفورس دي الايكويشن بتاعت الفورس ديريفاتيف، وبرده احنا خدنا ده قبل كده we already did go through all of this previously في الفيرست بارت how to get the first partial derivative, the second partial derivative, the third partial derivative at certain points. If you just remember all of this you will find all of this involved in our work previously. Now we are discussing because this case will be repeated in several times as you will see. It's a very common case. Once you are working with one of the critical points is 0 and 0, you will have x minus 0, y minus 0 stand for u and v, and then it's gonna be for the second derivative f double x times x square over f of xy uv f double y v square. Then the third derivative will be exactly like this, and that's the fourth order derivative with just only the difference that u square v square is going to be x square y square because you are making the expansion from 0. Okay, now for this paragraph, which is important, it states that if a is a stationary point of a C2 function that can be differentiated for 2 times, with an open domain, so there is no restriction on the domain, and the Hessian matrix at F is non-null, and it is positive semi-definite or negative semi-definite, then A is respectively a local minimizer or not extremum, and the local maximizer or not extremum point. This is why we call it the system will be shutting down or inclusive, and we will need further investigation. Let's take this example, which for a function x to the power of 4, y to the power of 4 minus x minus y to the power of 2, this function maps stuff from R2 into R. As you can see, it's a polynomial, so it's a C indefinite, C infinite, so you can differentiate it. There is no problem with that. Okay, let's get the first order derivative in order to get the stationary point or the critical point. So differentiating with respect to x is going to be for x cubed. Then I will differentiate this guy, which is going to be minus 2 over x minus y. Then I will differentiate partial derivative with respect to y, which is going to come up to 4y cubed. Then same way like, which is going to be 2 over x minus y. This is the equations once you put them equal to 0. So it's going to come up to 4x cubed minus 2 over x minus y. And for the second equation, it's going to be, as you can see. Now I will try to simplify stuff. We'll try to make substitutions from each equation into the other So simply I can replace x minus 1 in the second equation by 2x cubed from the first times 2 once you substitute. So it's going to come up to 4y cubed plus 4x cubed equal to 0, which will let that in y cubed يساوي negative x cubed. That's y equal to negative x. Take this information and really let's substitute in the first equation. We will end up having this guy, which means once you take 4 of x as a common, we have 4 of x times x squared minus 1. That's the case. So you will have x equal to 0. That's a critical point. You will have x equal to positive 1, x equal to negative 1, and substituting in y minus x for these values, you will have your critical point. So the critical points will be 0 and the negative 0 and 0. Then if x is equal to negative 1, y is positive 1. Then if x is positive 1, y will equal to 1. So these are the values. And so you will have 3 critical points or stationary points. Points need to be investigated. They are probable candidates for extremum. So once more, doing exactly the same. This is also the shape, but from taking a photo or the shape of the function and from away, this is gonna be, or from the view is taking the picture in more details. As you can see, we have two peaks to this function, which increases rapidly. Okay, let's go first for the analysis when x equal to negative 1 and 1. Exactly the same way. This is the function. That's the stationary point. That's the gradient. All of this we have it before. I will start to differentiate to get the Hessian matrix. So we will start to differentiate with respect to x once more, which is going to develop 12x squared minus 2 for the double partial derivative with respect to x. And for an x and y, it will develop just only 2. Same way like for the second component, which will give us partial, the mixed derivative and the second partial derivative with respect to y, as you can see. Now, for the time being, I will start substituting by the critical point. Let's keep this guy away, and let's start by negative 1 and positive 1. Once you start by negative 1, positive 1, this is going to be positive 12 minus 2, which is 10. And that's also what's going to be 10. There's going to be 10, 2, 2, and 10. Here we go. That's the matrix that we are dealing with. I try to get the leading principal minors, which is going to come up to 10. And then also the second one is positive. So it's a positive definite situation. We are talking about local minimizer. In a similar manner, I will do the same, but with the Hessian matrix in the case of 1 and the negative 1, which is really very simple. All I have to do is once more try to substitute instead of x or y by the values of 1 and the negative 1. In the Hessian matrix, it's going to be 12 minus 2, which is 10, 2 and 2, and 12 minus 2, which is also 10, which will give exactly the same way. So we have a local minimizer. So for this function, we have two critical stationary points, and both of them are critical, are strictly local minimizers for this function. Now going to the critical point, which is at 0 and 0. For the point at 0 and 0, I will start to substitute once more in the Hessian determinant. Leaving x was equal to 0, y is equal to 0, I will have negative 2, 2, 2, and the negative 2. And this is the function that we are dealing with, as you can see. So now delta 1 is negative, delta 2 is equal to 0, and 1, 2 is negative. So it's a negative semi-definite according to the classification that we spoke about previously. Now I will need to do a further investigation for this problem in particular. So I will take minus 2u squared once more. Let's go to this guy. This is negative 2y squared, yeah, negative 2x squared. بعدين 4xy. بعدين الجزء الاخير negative 2 in y square, which can be put in a perfect if you take negative 2 as a common in the case of a perfect square, which leads to u equal to v. That's the main shape of the quadratic form. So maybe at 0 0 local maximizer because it's a negative semi-definite, maybe a local minimizer, or not an extremum at all. So we will need to go through deeper analysis as we spoke previously. For this deeper analysis, we will need to study higher order derivatives of this function. And based on this, so if you read this paragraph, if A is a stationary point of a sufficiently differentiable real function, if with an open domain, the Hessian matrix is non-null, but it's a positive semi-definite or negative semi-definite, and the first non-null differential of f is at A is، خلي بالك الفيرست ده ما هواش، ابدا ابص بقى على الفيرست نون null partial derivative. تاني يا شباب، انا عندي الاف دبل داش عند البوينت دي failed، وبالتالي ببدا اكمل عشان هما نيجاتيف سيمي ديفينيت، فببدا اكمل زي ما هتشوف. هروح بقى اجيب اول تفاضل مش بيساوي زيرو، the first null differential of A. لو هو odd يبقى على طول for at least one singular direction، يبقى على طول it's not extremum point of f. لو الفيرست null. If it was even either negative or positive for at least one singular direction, you're not an extremum. اوكي، طيب خلي بالك لو هو even order وكان positive value او negative value، لازم الاوردر بتاعي ده مهم جدا بالنسبه للفيرست الايفن، لو هو positive او بعدين او negative for all singular بقى directions، لكل singular direction هو positive او negative for all singular direction، يبقى ده على طول لو هو positive اديني local minimizer، لو negative اديني local maximizer of v، وعلى طول ده هيديني لو في الاول في الاول دايركشنز الكيس which is in front of us. اوكي، extremum point semi definite or semi differential. نبقى نشوف الكيس، نرجع تاني للكيس اللي احنا كنا بنتكلم عليها. ادي الفانكشن بتاعتي ده الهيزيان ماتريكس. ريمبر at 0 0 لما كنت باجي احسب ده، اولا بيطلع نيجاتيف سيمي ديفينيت، بس الديترمنت نفسه بيساوي 0. نيجاتيف 2 تايمز نيجاتيف 2 4 ماينس 4 هيديني 0، which means the second order derivative is equal to 0. once ان السكند اوردر ديريفاتيف بتاعك is equal to 0، هحتاج بقى دلوقتي ان انا امشي في further analysis يعني ايه ستيب باي ستيب. يبقى ده معناه ان انا هحتاج الثيرد اوردر ديريفاتيف، يبقى 0 0 local maximizer or not extremum point of g. اوكي، هروح بقى singular direction وليكن u v، اختار اي singular direction وليكن u equal to v. لو انا inserted u equal to v in this equation هلاقي الاتي. اول حاجه انا بختار بقى اي singular direction، لو اليو بتساوي الفي، الاكس بيساوي الواي. بعدين اروح اجيب بقى الثيرد ديريفاتيف، لان السكند ديريفاتيف بيساوي زيرو، فعشان اجيب الثيرد ديريفاتيف هبدا differentiate 12x square minus 2 once more, so it's gonna come up to 24 of x. التو سايدز هيبقوا بزيروز، لو انت بتعمل مرتين لاكس ومره لواي، او مرتين لواي مره لاكس هيبقوا بزيروز. لو انا عملت السكند اوردر ديريفاتيف بالنسبه لواي هيبقى 24 of y. لو انا جيت اعمل سبستيتيوشن at 0 still الثيرد اوردر ديريفاتيف كله على بعضه يساوي 0. just a second، خليني انزل ده كده عشان الاضاءه عشان الجلير، ونبدا نشوف او نكمل. خلينا نشوف كده، ترى كده احسن. اوكي، طبعا ده ثيرد اوردر ديريفاتيف. I'm really very sorry for the long video, but it's a must. It covers a lot of things, and it has to be all together at once. We will have to go through it all together at once. So once more, the second order derivative is equal to 0. I've tried to get the third order derivative, and once you start substituting at the point 0 and 0, the result will equal to 0. So يبقى الفيرست اوردر ديريفيتيف السكند اوردر ديريفيتيفز equal to zero. لما جبت السكند الثيرد اوردر derivatives also equal to zero, so I will need to do further investigation and get the higher another higher order. Okay, that's the third partial derivative, which is equal to zero. I will have to differentiate it once more. So I'm going through the fourth derivative. I will differentiate 24 of x is going to be 24. I believe this is the last one. Those are zeros. This is going to be 24. Although we are going to the fourth derivative, but the good news is a lot of these partial derivatives will vanish at the point that we are examining, as you can see. So now the fourth order derivative is 48 u to the power of 4, which is 48x to the power of 4. And so once you start substituting, I'm sorry, that's the a at the point 1 and 1 in a specific any point in the direction of x equal to y, it's gonna be a 48. So once you start to see here the analysis, okay, at 0 and 0 في واخترت point من points in one singular direction, it's 48 greater than 0. So extract local minimizer of g in the direction of 1 and 1. Okay, same way like at other points, it's gonna be not a maximizer, it's gonna be a minimizer. Here it's a minimizer. In the non-singular direction, we found that it's a maximizer, so it's a saddle point at the point 0, 0. Uh, Another way to go through all of this, but just to avoid the complexity of having the third order derivative, especially in the multivariable functions, or in the, to the third, fourth, and so on, we can do the following. Here is the Hessian matrix for the problem that we are really studying, and it's negative semi-definite. The determinant value is equal to 0. To avoid the complexity of higher order derivatives, we may consider restriction of the domain. Instead of waiting for the restriction till the last point, I can do some construction on the domain and try to simplify stuff a little bit. So here's x4 plus y4 minus x minus y to the power of 2. Remark, this polynomial can be separated into a quadratic part and not a quadratic part. The quadratic part, which will develop the quadratic form, is negative x squared plus 2 over xy minus y4. So if you take a d block for this guy and taking negative as a common, I can simply put it on this form. The first quadratic part, which is negative x squared minus y squared plus 2 over xy, if you take negative as common, it's a perfect square of x minus y to the power of 2. And the 4, this is also a typo here. This is the non-quadratic quartic. This is the quartic part or the non-quadratic part. I would prefer to call it like this, not the quadratic part. Here it's a quartic part because it's a x to the power of 4, y to the power of 4, as you can see. Now I will start to analyze behavior near the origin, the point that we are studying, okay, for limit the variables of x, y tends to 0, 0, or taking small values at the point of 0 and 0, as you will see. So simply all I have to do, let's take few passes. I would suggest x equal to y, and that's the very famous one. It will simplify our life greatly. So if I use x equal to y and start to substitute, I will end up having 2x to the power of 4, which means in this direction, f is greater than 0 for small values of x. And once f for here, it's greater than 0. If I used another row, which is x minus y, another path, and start substituting in f, I would have x 2 of x power 4 minus 2 of x to the power of 2. And here, the governing part for this relation near the 0 will be the negative 1. because of course if you have like zero point 0.5 to the power of 2, it's going to be 0.25, but if you have zero point 0.5 to the power of 4, you will have a smaller value than this one. So the result, or the dominant name, will be the dominant term, I'm sorry, will be the negative. So it's less than 0 for small values of x. So it's a saddle point. Of course, the function takes both positive and the negative values arbitrarily close to the origin, which means it's a saddle point. The problem here, as I told you, the problem here is the difficulty here is to, or the difficulty in this method is to find the right restriction that will help us getting what we really need. This is the only restriction. But imagine instead of getting the third order derivative, the fourth order derivative, all I had to do is just going through these procedures, trying to take a deeper look for the function by itself, try to choose some restriction on the analysis, and then it will be verified. Now for the nullity and the differentials of summarizing this steps. If A is a stationary point of A sufficiently differentiable of real function with an open domain والهيزيان matrix is null، يعني المشكلة بتاعتي ان الهيزيان matrix at this stationary point is null, and the first null differential of f at A is لو هو of odd order at least in one direction يبقى على طول عندي not extremum point. طيب of even order لو عدد التفاضل ده even for all direction but positive in some and negative in others يبقى not extremum point. These two cases will lead to the same. This is when the order of derivative, the first non-null is odd or the first non-null is even, they will be like this. طيب لو انا عندي بقى الفيرست non-null is even يعني force يعني sixes of the same order and the positive، خلي بالك of the same order and the positive for all direction will have strict minimizer. لو هو negative for all directions يبقى maximum of f a maximizer of f. طيب of even order and the positive for all direction but of different orders, not extremum for all directions but of different orders, okay, not extremum point of the local minimizer or so that's the bottom line of this. Let's go for this problem, which is x to the power of 4, y to the power of 4, and apply the knowledge that we saw previously. That's a function which from R2 into the domain, it's a polynomial, so it's a C infinity. I'll try to get the first derivative, which is 4x cubed or y cubed. Once you get these two guys and equal to 0, so the stationary point will be at 0, 0, just only one critical point, which is 0 and 0. We'll try to get the Hessian matrix in order to do this classification, which is going to be 12x squared, 12y squared. Once you substitute by the stationary point in this Hessian matrix, the problem that we are talking about happened already, and it is disappearing. The determinant is equal to 0. Now we will go for the third order derivatives. Once more, it's going to be 24 of x and the 24 of y, and I will do the derivative or the third derivative formula around 0. So it's a f triple x cube, 3 of f triple of x square y and the xy square and y cube. And also once you start substituting, you will end up having 0. So one of the first odd is null. I will have to differentiate more. Once more, the good news is 24 of x, that's the only guy that will appear. 24 of y, that's the only guy going to appear. Other than that, it's going to be zeros. So doing so, once more, getting the fourth derivative, as you can see, and start substituting by all of these values, I will have that 24 x to the power of 4 plus y to the power of 4, which means at 1 and 1 or so, it's going to be a greater than 0. يبقى the first non-null derivative is even. أول non-derivative is even. And for any value other than that zero it will be positive. يبقى إذا أنا عندي local minimizer of f. Straightforward. Okay? And that's a very good example on the case that we explained in the previous slide. Uh, Please do some problems. We have some problems on the model. Please do them. You will find them in the video, I believe, or on the main slides. So please try to go through them. That's an analysis for these functions. Try to link each one of them, which is suitable when you get time. This problem also is very nice. I've solved it with you, and I have a couple of comments about this problem. I want it to be clear to you. Please be careful once you start solving such problems or answering such problems either on SBE model or whatever, because sometimes your mind will be stuck in some direction, and once you start answering, you may do some mistake. I do some of these mistakes, silly mistakes too. So please be careful, take your time in thinking, and everything will be okay. I've solved the previous slide for you. So f is a polynomial function. Its domain, which is y power 4 minus x power 4 y square. There is no restriction whatsoever on the domain. The gradient vector is minus 4x cubed, 4y cubed, 12y, and the stationary points are 0 and 0. The Hessian matrix, as you can see, and the leading principal minors of this matrix are in increasing order, which means we need the remaining principal minors of the matrix, which is going to come up to 12. Overriding or overviewing the sign, it's solved, so you can review it. I don't want to increase the time of this video going through all of this. But the two remarks that I want you to see here, I made, I was going to choose negative the value, but I did it rapidly, so I have a wrong answer here. And here also it's a strict local minimizer. These are the two comments. Please try to do this once more, and when you get time, inshallah. Okay, the convex, and now I want to talk with you about the global extremum analysis. And after this, I will talk with you about the envelope theory, which has a lot of applications. This part is really very simple. If you have, for example, p of x, so let me read this paragraph first, and I will explain these examples for you. It's really very simple. If a differentiable function f with an open and convex domain, convex or concave, then any extremum point of f is a global minimizer of f. If f is differentiable and strictly convex or concave, then the stationary point of f is a strict global extremum of point. That's the case which will happen when you don't have a restriction. So for this guy, for example, y equal to e power x, which is increasingly from on the open domain, is strictly convex. If it changes its gross orientation 0 times, it has no extremum. This function has no extremum. It change the convexity of the curve of this curve from the negative infinity to positive infinity. On the other hand, for y equal to x squared, the function changes its monotonicity from decreasing into increasing, and so with an open domain, you will have a local and a global minimizer for this function. So it's a strict global minimizer. Okay, in this case, you have also, it's an infinite and it's an open domain for h cube. You will have a minimum and a maximum, but both of them have a local maximum, local minimum, but not globally. Okay, because the domain is not restricted of this function. So it will increase till infinity. So you have just only local minimum and a local of a maximum, but not globally. Okay. This is also the analysis stack to convex function changes its growth orientation at once. Any minimizer of I is global. This is an example of R2, which is from R2, I'm sorry, which is 1 minus 2x squared minus 3y squared. Once you get the gradient vector, you do the Hessian matrix. It's a negative symbol, it's a negative definite, so it's a strictly concave function. And remember that since it's strictly concave curve and it's an open domain, so it's strict global maximizer. If I want to uh, 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 go through the study in depth of pointers of globality of an extremum or extrema point to analyze its extremum if it is global rather than just only local, we will need to go through this analysis. First of all, identify the domain. You will have to identify the domain of your function. Then find the critical points, which is local extremum, as we did previously by getting the first order derivative, putting it equal to 0, and so on. Use the second derivative test. Analyze the boundary. ابدأ بص على الباوندري بتوعك. If domain is bounded or constrained. لو في restriction على الباوندريز أو الدومين هيبقى much easier إنك تقدر to identify الكيس. Consider behavior at infinity. Consider انك تعمل الليمت بتاعت الفانكشن بتاعتك tends to infinity وتشوف البيهيفير بتاعها especially in case of an open domain. Apply the Weierstrass theorem if applicable, and we will talk about this shortly. Compare values. اعمل مقارنة بالvalues around the stationary points or around the boundaries. In specific, ده يعني a little bit more description for each step, for each point, I'm sorry. So identify the domain, check if it is open, closed, bounded, unbounded. All of this will be a function with you in determining the nature of your classification. Find the critical points, okay, of all variables. Use second order in order to know the nature of these critical points. Analyze the boundary, arbitrarizes or apply constraints if needed. You have to analyze your boundary. Consider behavior at infinity. Check limits of domain is unbounded, indicate unbounded. If f is continuous on compact set, extrema exist. لو هي continuous على compact set يبقى الاكستريما موجودة. Compare all values of f, all critical and boundary points، وبالتالي اقدر نتيجة الكومباريزون دي اقدر اعرف اذا كانت global ولا مش global. Identify the domain in much wider look. It means open or closed, bounded or unbounded, compact, closed, and bounded. Important for global extrema via Weierstrass theory. Find the critical points, putting gradient vector equal to 0. Use the second derivative test for the fitness of the Hessian matrix if apply. Analyze the boundary if the domain is bounded or constrained. If the function is defined on a closed boundary region, this rectangle extrema may occur on the boundary. I'm sorry. Okay. The fifth step, consider the behavior at infinity in case of open domains. When the function goes to infinity, let's study the case. Okay, apply the Weierstrass theorem if applicable. If f is continuous on a compact set, then global maximum or minimum exists. Compare function values at critical points and the boundary point and find the absolute global extreme. And last, compare values. Largest value is going to be global maximum. Smallest value will lead to global minimum. That's the analysis that we will need. Let's do this on an example. He is giving you discuss the global extremum of the function x square y square, and the domain is closed disk, which is x squared plus y squared less than or equal to 1. So now I'm studying the case of the extremum of x squared plus y squared, but just only on the case of x squared plus y squared less than or equal 1, which is a disk. The domain number 1 is closed and compact. It's the inside of the unitary circle or the unit circle. The critical points for x squared plus y squared, once you differentiate with respect to x and respect to y, it's going to be double zero. Because the first partial derivative with respect to x squared is 2x. The first partial derivative with respect to y squared is 2y. Putting them equal to 0 will lead to x equal to 0 and y equal to 0. Second derivative test, f double x is going to be 2, f double y is going to equal to 2. So the determinant value is 4, and we have a local minimum at 0 and 0. Now I will need to do further analysis to know if this local minimum is a global or not. Let's look to the boundary. The boundary is x squared plus y squared equal to 1, which is a circle. And these are the circle on the boundary. Any value, okay, compare values. If at 0, 0 for this function, it's going to equal to 0. But if you, and on boundary, it's going to equal to 1. لو أنا جيت عند 0, 0 وبشتغل على الفانكشن بتاعت اكس سكوير واي سكوير the result will be 0 but on the boundary is gonna be 1. global يعني ده معناه ان الفاليو which means that the value of the function at the critical point is less than the value at the boundaries. يبقى اذا ده معناه ان انا عندي global minimum at f 0 0 والفاليو بتاعته بتساوي 0 وجلوبال ماكسيمم on the boundaries هيحصلوا عند القيمه بتاعت f equal to 1 in specific. طبعا هنا البوينترز بيقول if possible prove that local extremum of a real function f is global or not. لو انا عايز اثبت ده for example studying the general expression of f, study الحالة العامة بتاعت ال f, comparing images of f or computing limits of f. على ان انا اقارن الليميتس بتاعت ال f وكمبير الليميتس بتاعت الايمج زي ما انا قلت من شويه. المساله دي ظريفه قوي. المساله دي فيها ln of an x square plus y square minus 4x plus 5, which is a combination between two things. First of all, the domain from R2 into the domain of G, and it is open. لاحظ انه the function inside, that's a composite function. The function inside the logarithmic is a polynomial and it is of C infinity, so x square y square minus 4 of x plus 5. And we have the ln of A. So this is C infinity open domain. But for the ln to work, the input function must be greater than 0. So a polynomial and a logarithmic and f composite of h وجي I composite h. ما عنديش اي مشاكل whatsoever بالنسبه للدومين restriction بتاعي ده from R2 into R، واللي انا عشان اشتغل بياخد الار بوزيتيف بس ما باخدش الار نيجاتيف. يبقى اذا حددت الدومين بتاعنا. روح بقى هات الجريدينت فاكتور. عشان to get الجريدينت فاكتور I will differentiate the function once with respect to x and once with respect to y. And once you want to find the critical points, you will put these two components equal to 0, which means the denominator of the first component equal to 0, the denominator of the second component equal to 0. This is going to be at 2 and 0. We have just only one stationary point, which is at 2 and 0. Let's go for the second order derivative. I've already made the second order derivative and simplify it as much as possible. Let's start substituting by 2 and 0 on all of these guys. So the y will disappear. Just only substitute by the value of x. This is going to be 0. That's going to be 0. This is not going to be 0 and that one too. So start substituting. I will have that f double x equal to 2 and f double y equal to 2. So this guy and that guy at the origin is equal to 2 and the others is equal to 0, which means that the determinant is greater than 0 and f double x is greater than 0. We have local minimum point at 0 and 0. Now to the question, is it global or not? Okay, that's the positive definite, and that's the case we are talking about. Check for global extremum. That's the function. Determine the domain. The function involves a logarithmatic, so the argument of the logarithmatic must be strictly positive. So let's take a deeper look for the argument of this domain, which is x square, y square minus 4 of x plus 5 is greater than 0. That's the one that we have. We can collect the x square term, x square minus 4 of x plus 4. This will leave us with 1. So complete the square, and we will get the form that I show you above, which is x minus 2 to the power of 2 plus 1. Okay, so the inequality becomes, this inequality becomes, as you will see for the time being, x minus 2 to the power of 2 plus y square. And you need to see what's going to be the case of minimization at that point. So at x equal to 2 and y equal to 0, this part from our expansion will be 0. And the ln will equal to 1. And once you have ln equal to 1, the result will be 0. So simply just making a substitution of 2 and 0 near the point that we are talking about, you will have ln equal to 0, ln 1, and it's equal to 0. Taking limit of x tends to infinity for x minus 2 and y square, all the values will grow to infinity. So this graph means that the function has a global minimum at 2 and 0 with no global maximum, because as x and y tends to infinity, the value of the function tends to infinity. Back again to the function x cube y cube minus 3x squared 3y squared, and let's do the analysis once more to discuss if these points, the critical points, are local, just only local, or global extremum. The gradient equal to 0. The stationary point is those points. This is the example that we solved already. Okay, at F, that's the Hessian matrix. That's the shape of the Hessian matrix. At 2 and 0, we have local minimizer with a value of negative 4. Okay, strict local maximizer 0 and 2, and the value of positive 4. The Hessian matrix is negative 6 and 6, not convex or concave. Now studying the general expression of F comparing images، بقارن بقى دلوقتي عشان اعرف اذا كان ده global ولا just only local for these two guys اللي هو 2 0 0. So let's consider، عايز استدي الكيس بتاعت الدومين ده لما هروح لانفينيتي لانه open domain. انا هعمل ايه؟ هعمل restriction على الدايركشنز بتاعتي. I will do a restriction. I will put x equal to 0, and let's discuss the case when y equal to infinity. Once you do this, y equal to y tends to infinity while x equal to 0, and the substitute in the main function, which means that all x equal to 0, and this is minus y cube plus 3y squared, and they are getting to infinity. The dominant part will be the negative sign, so it's a negative infinity. So if reaches negative infinity, it has no global minimizers. يبقى y رايح لبوزيتيف infinity، الفانكشن بتروح للنيجاتيف بارت، no global minimizers. And for the other direction, putting y equal to 0, taking x equal to infinity, I will have x cubed minus 3x squared, which is going to positive infinity. So we will have no global maximizer for the function. Guys, now I will talk about the envelope theorem in unconstrained optimization, one of the best examples ever that and the parts that really exist, and we need to talk about. This is really very interesting. The envelope theorem in economics and optimization, it's a powerful result that simplifies derivative calculations when optimizing functions with parameters that will change. In economics, the envelope theorem helps us understand how the optimal value of an objective function like utility, profit, cost how the action of this function changes as external parameter change. يبقى انا هيساعدني ده الانفلوب theory اني to speculate the behavior of the objective function without resolving the problem once there is minor changes of an external parameter already embedded in our solution without needing to complete. It's used in optimization problem of course. اول حاجه maximize or minimize الفانكشن اللي هي f of x and alpha. alpha ده represent البارامتر specific اللي انا بدرسه with respect to a decision variable x, and we are interested in how maximum value changes as the parameter changes, like price, like another new law appears, will affect your production and so on. Here we go. We could determine for an optimization problem after being solved. يعني على فكرة ده أنا دايما بقول عليه جزء من السنسيتيفيتي اناليسز related للسولوشن بتاع أي optimization problem. It's really a very good part to go through it, trying to explain what happened to the model if there is certain changes happen. Okay, here we go. If something changed, what's going to happen in the value of our optimization problem? Without resolving, that's the condition, without resolving, so it has a huge impact and benefits, especially in the complicated models of optimization. Okay, the mathematical statement for single variable function. I have f of x and alpha, differentiable function defined. I will need to get v of alpha. V of alpha, it means the value of the function that you are optimizing, but at the critical point and with the appearance of the new parameter that you will make your analysis at. يعني الفي ده هو الداله اللي انت بتعمل لها اوبتمايزيشن عند الكريتيكال بوينت اللي انت عملت عليها الاناليسيس. ما هو الجزء بتاع الانفلوب ثيوري ده ما بيحصلش الا لما تكون خلصت المساله اصلا وحلتها وجبت السولوشنز، يعني عندك الاكستريمم بوينت وبتعمل فurther اناليسيس او في تشينجز في الموديل as we will see. دوت الاف at x and alpha. Let x alpha be the optimal x that solves the maximization problem. Then the envelope theorem says that dv by d alpha بيساوي partial f partial alpha، والاف دي الفانكشن اللي هي maximized or minimized. v ده الفاليو of this function at the critical point. هنا هعمل السبستيتيوشن x بيساوي x star. اوكي in words explanation بتاع ده بالكلام in words the rate at which the maximum value changes with respect to alpha is just the partial derivative of the objective function with respect to alpha evaluated at the original the optimal point. يعني لازم اكون عملت الاناليسيس بتاع الفانكشن، جبت الاوبتيمال بوينت بتاعتي، كل المعلومات موجوده معايا، عملت اناليسيس، يعني عملت الاناليسيس بتاع الفانكشن بتاعتي already solved حليته، وعارف الاكستريمم، عارف البوينتس اوف اكستريمم بتاعتي، البوينت هل ده maximization minimization problem what's gonna be. After doing this, the external parameter that's involved in your solution, it has some changes and you need to see what's gonna be. Okay, perfect. Let's study this example. It's a profit maximization of a small firm with one product. Let's suppose that a firm chooses output X to maximize the profit. يعني أنا بختار واحد من البرودكشن عشان to maximize the profit بتاعي. الحالة دي هيبقى البروفيت بتاعي بيبقى عامل إزاي؟ بيساوي الريفينيو فانكشن minus التوتال كوست فانكشن as usually know. طيب B of X، طبعا الإكس دوت الكوانتيتي produced، B ده البرايس اوف ذا برودكت، ده البارامتر اللي انا اتكلم عليه لو حصل change of prices. Number 2C is the cost of the function that the cost of the function that we are interested in. على طول الحركه اللي بعديها let's define the profit function that will be maximized, which is bx minus x squared. That's the function that we need to maximize. So I will start differentiating this function with respect to the production. The put it equal to 0. Here we go. With respect to x, so it's going to be b minus 2x. Once we have the first order derivative, we will insert it equal to 0 in order to get our stationary point or the critical points, which will let us have x will be maximized, or there is a stationary point when x is p over 2. Try to get the second order derivative of this guy, which is going to be -2, which means it's a maximizer. So now أنا دلوقتي عندي أقدر أجيب الفاليو بتاعت البروفيت maximum at P over 2. يبقى for a decision variable or a production of P over 2, the maximum value will be B square over 4. That's the profit of the function. دلوقتي أنا معلوماتي إن الأوبتيمال بوينت هتحصل عندي B over 2 والأوبتيماليتي فاليو بتساوي B سكوير over 4. طيب لو السعر بتاعي تشينجد بدل ما كان بي بقى بي بلس الفا، what's gonna happen؟ اولا الفاليو بتاعت الباي البروفيت هتتغير، هتبقى بي بلس الفا في اكس ماينس اكس سكوير. وخلي بالك انه لما بعمل كده اهو، ده هنا الابلاي بقى الانفلوب ثيوري. لو انا دلوقتي انا خلاص عرفت الاوبتيمال فاليو بتاعت الفانكشن بتاعتي، وعرفت ان ده هيحصل عند في اوفر 2. خلي بالك ان لو انا كنت مسكت الفي اللي هي الفاليو بتاعت الاوبتيمال فانكشن بي اوفر 2، which is هتبقى بي سكوير اوفر 2 ماينس بي سكوير اوفر 4 بي سكوير اوفر 4، وعملت لها ديريفاتيف وذ ريسبكت للبارامتر اللي هو البي هيديني بي اوفر 2. يعني لو انا خدت بي اوفر 2 وعملت بيها سبستيتيوشن في المين فانكشن هيديني نفس الريزلت بالظبط، وبالتالي ده success because they have the same value. So that's the derivative of the value of the function maximized at the critical point, which is half p. لو انا خدت الفانكشن بتاعتي الاساسيه وعملت لها derivative with respect للبي كان هيديني x. لو شلت الاكس وحطيت p over 2 هيديني نفس الفاليو. So it holds at this at now without needing to differentiate x 0, which means انه they have the same value. summary of law enveloped theory. انا حسيت ان انا محتاج ان انا اكتب لك القانون بالشكل ده وابلايت على المساله اللي هتشوفها، هتلاقي الامور سهله جدا. هنا بيقول in an optimization problem the derivative of the value of function with respect to a parameter equal to the partial derivative of the objective function with respect to the parameter evaluated at the optimum. I will repeat it once more. تاني، الانفلوب ثيوري بتقول an optimization problem the derivative of the value function، يعني بيبقى عندي الفانكشن بتاعتي وعملت لها derivative with respect to the parameter equal the partial derivative of the objective function with respect to the parameter evaluated at the optimum. كمل. we can use ان الاوبجكت فانكشن b plus delta b، يعني ده الجزء اللي حصل فيه التشينج، will equal approximately the value of the objective function at the maximum point plus اعمل partial derivative للاوبجكتيف فانكشن عند البارامتر واعمل بي سبستيتيوشن عند البي ماكسيمم واضربه في الدلتا بي. بس كده، كده انا قدرت اجيب اللي تشينج او الاكسبكتد تشينج في الاوبجكتيف فانكشن نتيجه اللي تشينج ان ذس بارامتر. بص على المساله دي بسرعه. هنا بيقول in a production of a cherry fruit in a cherry farm Q is the produced cherries in kilograms and the price of each kilogram is 10 minus Q euros. So that's the price as a function in the quantity. The cost function is 2Q وده الكوست فانكشن. خلي بالك ان انا مدي لك البرايس ذا فانكشن ان ذا كوانتيتي، بالتالي انا عايزك تعمل ايه؟ maximize البروفيت اوف this function. يعني ده معناه ان انا لازم اجيب البروفيت فانكشن الاول، بعدين بعد ما اجيب البروفيت فانكشن واحل واجيب الماكسيمم. I want you to discuss study the case. What's gonna happen if instead of 10 it's gonna be 10.5 minus q by applying the envelope theory. First of all, let's summarize everything. Q is the quantity of shares produced in kilograms. يبقى الكيو ده الكمية اللي بيتم إنتاجها. الحركة اللي بعديها البرايس هو 10 minus Q euros. يبقى ده معناه ان الريفينيو فانكشن simply كل اللي هيحصل ان انا هضرب البرايس في الكوانتيتي which is BQ times Q which is gonna be 10 minus Q times Q. يبقى ده بيريبريزنت الريفينيو فانكشن. وهنا I بيفورميوليت المسألة، يعني بيسايد ان انا بعمل اوبتمايزيشن، لا ده انا بوجد الفانكشن اللي انا هعمل لها الاوبتمايزيشن from the scratch. يبقى ده 10 minus Q times Q which is gonna come up to also the cost function is given which is 2Q. يبقى اذا البروفيت فانكشن بقى اللي انا هعمل لها الاناليسز هي الديفرنس between the revenue and the cost function. So it's the difference between 10 minus Q times Q which is 10Q minus Q square minus 2Q. So that's the by of X or the function that we will need to optimize for the first question. Simplifying the stuff, it's gonna be 8Q minus Q square. فأنا عايز بقى إيه to maximize or to get an extremum for this point. I will differentiate once, putting the derivative equal to 0, getting the second derivative, and getting the point that we are seeking. Derivative with respect to the quantity, it's gonna be 8 minus 2Q. Once you put it equal to 0, the quantity is gonna be 4. That's the star quantity or the stationary point. If you make a second derivative, it's going to be negative 2, which means at Q equal to 4, you will have your maximum profit. It's not just only this, but if we substitute by 4 in this profit function, we will get the maximum profit. So bottom line now, I've completely solved the problem. The first part is already done. The maximum will happen when the production is 4 units, and this value will be 60. Now I will need to discuss the case of increasing the price, or there is a change in the price function to be 10.5 minus value. I will suggest going through this because this is a problem we need to explain. So I will say that the parameter will be the change with 10. What will happen in this parameter? So instead of having the price which is 10 minus Q, I will put it as alpha minus Q. This is for the explanation only. But for the solution of the problem, you will see it's very simple. So that's the price. So originally alpha is equal to 10, and the alpha will change to be 10.5. That's the parameter that will change. Okay, perfectly. Then the new revenue function is alpha minus Q times Q, and the profit function will be on this form. This is if I started my deviation from the beginning. This is the value of the function, the maximum value. Now let's apply the envelope theory. I will try to get dv by d alpha. So differentiating with respect to alpha, you will end up having a q. Now let's start using the formula that I've given you or summarize it for you. By alpha plus delta alpha when the value is optimal is equal to. So now I'm going to study the case. 10 plus 0.5, which is 10.5. That's the change that happens in the parameter alpha. It will equal to approximately the value of the profit with the original value plus partial derivative of the parameter times delta V, which is the approximation formula that we will use. Remark that the partial derivative of pi with respect to alpha is simply it's gonna be q, and at the maximality point q is equal to 4. Now the delta alpha, which will change, is 10 plus 0.5, which is going to be 10.5. Now the value of b at 10 which is 16. The value of delta bit equal to 0.5. All I have to do is to make the substitution. This guy is going to be 0.5. The partial phi, partial pi, partial pi is going to be 4. The value of the pi function or the profit function is originally by 16. So changing from 10 to 10.5 will make you gain 2 extra units just by the direct substitution. That's at 10.5. It's going to be 16 plus 4 times 0.5, which is going to come up to 18. And that's the effect that you will have on the maximization, on your maximization problem. Very simple. Thank you very much, and I'm really very sorry for the long video that I had to record for you to cover all the ideas of the previous slides. Thank you very much. Please feel free if you have any questions or anything. Please do not hesitate to send it to me. I've sent you the slides as PDF, and also you will have this video available with you. If you have any questions, you are more than welcome. Thank you very much. And if you have any comments, please don't hesitate to leave it on the comment line. I appreciate so much your time, and I hope this video helped you in understanding the analysis of the multivariable functions, especially if we are trying to seek extremum and the optimality for the unconstrained situation or function. Thank you very much, and enjoy the rest of your day. Thank you. Appreciate that so much. Thank you. Bye bye.